Hello, everyone. Welcome to the analysis seminar. We're happy today to have Norm Levenberg from Indiana University, and he's going to tell us about zeros of random polynomial mappings in several complex variables. Take it away, Norm.
The invitation. It's good to see your little boxes at least. So yeah, so I'll talk about random polynomials, and feel free to interrupt with questions. Vous pouvez poser les questions en français ou en anglais. Ça m'est égal. Okay, so this is what I'll talk about is eventually joint work with Turgay, Bayraktar, and Tom Bloom. And here's the general setup. So here's some notation. So calligraphic P sub n here is it's the holomorphic polynomials of the degree at most n in D complex variables in CD, and we'll let M sub n be the dimension of that vector space. So it's of order n to the D. And so our setup will be, if we start with a sequence of basis polynomials, or the space of all polynomials in CD. And I put in red here relative to a compact set K and CD, and you'll see what I mean. So there's going to be an underlying compact set. This basis is going to be related to this compact set in certain ways. And anyway, given this basis, then we form sequences of random polynomials. Hn here will denote a random polynomial of degree n. So this simply means it's a linear combination of those basis polynomials for graphic P sub n with coefficients ai that are random complex valued random variables. And these a sub i's will actually be independent, identically distributed random variables. And so for each n, we take a random polynomial, and we'll sometimes, to denote the underlying, the randomness here, we might sometimes also include this little omega to denote this, that these HNs are random. So I'll say more about the AIs and the PIs in a second. Okay. And the important thing we're interested in is if we look at, say, Hn, this random polynomial of degree n, form this associated plurisubharmonic function, which would be subharmonic in one variable, where we take 1 over n times the log of its modulus. We'll call that function u sub n. So it's plurisubharmonic, like I said, in several variables, subharmonic in one variable. Plurisubharmonic, if you are a one variable person, just means you're subharmonic on complex lines and your upper sum continuous overall. But these plurisubharmonic functions are a little more special because they grow logarithmically. To note this special class of plurisubharmonic functions in the whole space that grow most logarithmically by L of CD, the so-called the long class. And if we're in one variable, of course, you have this miraculous fact that in one variable, polynomials factor. And so in one variable, if the znj's are the zero of your random polynomial Hn, then the Laplacian of this subharmonic function un gives you the so-called normalized zero measure of that random polynomial, as it puts mass 1 over n at each of those zeros. And I could be off by 2 pi. We'll just take our normalization, so the Laplacian is exactly this. And if you're in higher dimensions, the appropriate operator to look at associated with this function u sub n is what we denote as DDC of u sub n, or more precisely here, it's 1 over pi times curly d bar of un. So this is a 1-1 current whose coefficients of dzj, which dzk bar, these are just the elements of the complex Hessian matrix of u. And this DDC of this u sub n is the so-called normalized current of integration over this algebraic hypersurface, or the zero set of Hn. And what we're going to care about is basically L1 Loc convergence of a sequence of these u sub n's associated with a sequence of random polynomials u sub n to a certain extremal function, a certain target function, which I'll call V sub k. And this is to denote there is going to be an underlying compact set K, which will come in the next slide or two. Okay? So more precisely, do we have L1 Loc convergence, the sequence of these so-called random plurisubharmonic or one variable subharmonic functions to this target function V sub k and L1 Loc in some type of probabilistic sense? And the two types we'll talk about today are either in probability or almost surely. And again, we're going to need under appropriate hypotheses on these independent identically distributed random variables, these AIs. And so I just want to make one comment that we're going to consider these u sub n's, and how I've indicated again the dependence on the randomness here. These are L1 log valued random variables here, so that what it means for this sequence u sub n to converge to v sub k in probability means that every subsequence of the UNs contains a further subsequence, which converges almost surely. Okay, so you'll see subsequences of subsequences coming in at some point. So the overall outline of my talk is we're going to talk about some deterministic results in so-called pluripotential theory of plurisubharmonic functions related to this mysterious target function v sub k that I haven't defined yet. And then we'll relate these deterministic results to some probabilistic results. So here's some motivation. If we take our random polynomial h sub n and form that random plurisubharmonic function u sub n, okay? So if I consider this collection of coefficients, these random coefficients, aj, as a vector, a random vector in CMN. Remember, little m sub n was the dimension of the space of polynomials degree at most n. So I consider this as a random vector, and this summation aj pj of z is a pairing of this vector with the vector of basis polynomials at the point z. And so if I form this unit vector by taking that vector of basis polynomials and divide by its little L2 norm, then and I'll call this summation of the moduli squared of these basis guys Bn of z. Okay, then this u sub n I can write in as a sum of two pieces. One is purely probabilistic. It's 1 over n times the log of the modulus of the pairing with this random vector with this unit vector, and the other is this term that comes from the b sub n. So I think I have my constants right. It's 1 over 2n times log of b sub n. Okay. The red part includes all the randomness, right? All the aj's. And the blue part, that just has to do with the basis polynomials that I've chosen, these pj's. Now, in the olden days, or if you wanted to describe results with respect to, for example, expectation results, this is a nice splitting, because if you want to take the expected value of this L1 of this random variable, this plurisubharmonic function, this plurisubharmonic valued random variable, you could take the expectation of this piece and add the expectation of this piece. But when we're talking about these notions of almost sure convergence or convergence in probability, we can't really split these two things apart so well. And indeed, what's going to be more relevant for us today is not this equality, but an inequality. So we can use Cauchy-Schwarz to get an inequality. That is, I just do Cauchy-Schwarz on the sum of aj pj's, and I can write an inequality that our u sub n, random plurisubharmonic guy, is less than or equal to this probabilistic piece, the red piece, plus this deterministic piece, the blue piece, 1 over 2n log bn. So if we know, so this gives us an upper bound, that is, if we know that the blue piece, this deterministic piece, converges to some standard thing, again, which will be to come, then if these random variables are such that the red piece, the probabilistic piece, goes to 0 in the appropriate sense, then at least we'll have an upper bound. The lim sup of this sequence u sub n is dominated by this deterministic piece v sub k. Okay. Now let me go ahead and really tell you about this v sub k, and then we'll discuss what type of basis polynomials we're going to deal with, and also tell you what assumptions we want to make on the random coefficients. And one of the things, oh yes, and before I forget, these random coefficients are going to be assumed to be non-degenerate. And one of our goals here is to kind of get the weakest possible assumptions on the random coefficients so that we get the results that we want. So what are the v sub k's? These are going to be extremal plurisubharmonic functions in several variables, extremal subharmonic functions in one variable. So for a compact set that's, well, not pluripolar, just means there's no plurisubharmonic function that's just that's identically minus infinity on this guy. So a reasonable set. We're going to take an upper envelope, a pointwise supremum of the functions in that Lalong class, those plurisubharmonic functions that grow logarithmically, that are normalized to be less than or equal to 0 on the compact set. And this function we'll call v sub k. And you've seen this in one variable. This is nothing more than the Green's function for the unbounded component of the complement of this compact set K in one variable. Okay, so a standard example is you take the unit disk or the unit circle. In several variables, you take the closed unit ball or the unit sphere. This extremal function is just the maximum of 0 in log mod z. And for compact sets, actually, you don't need to look at this full collection of Lalong class functions, the plurisubharmonic functions of logarithmic growth, but only the ones that come from polynomials. So you only need to look at ones that look like, that are of the form 1/degree times the log of the modulus of a polynomial, where now, of course, the polynomial needs to be normalized, so its sup norm is at most 1. Okay? And if you accept this, then in particular, or take this as a definition if you like, then this extremal function v sub k agrees with the extremal function for the so-called polynomial whole of k, or the polynomial whole, excuse me, of k is the set of points where every polynomial gets no bigger in modulus at these points than it does on the compact set in sup norm. And for the rest of this talk, we're going to assume that our compact sets are nice in the sense of what we call regular, and that simply means that this extremal function v sub k will be continuous. That is, in general, when you take an upper envelope of a family of subharmonic or plurisubharmonic functions that are, say, locally bounded above, then the supremum need not be plurisubharmonic or one variable subharmonic, because it might not be upper semi-continuous. So in general, you need to take an upper semi-continuous regularization, take the smallest upper semi-continuous function bigger than that supremum, and that's what this star denotes. So just if you see this star, this asterisk later on, that's what it means. So we're assuming that this v sub k equals its upper semi-continuous regularization vk star. Okay. Now, in one variable, the Laplacian of this Green's function, of this extremal function, is the potential theoretic equilibrium measure for the compact set. That is, it's the probability measure on K that has smallest logarithmic energy. Okay. And note that if we define, I'll call this function phi sub n, if I take the sup of the moduli of polynomials degree at most n that are normalized to sup norm at most 1 on K, I call that function phi sub n, then from this characterization of v sub k above, these plurisubharmonic functions 1/n log phi sub n clearly converge to v sub k pointwise. But if this function v sub k is continuous, which we're assuming, that actually this convergence is locally uniform. Okay, not too surprising. The reason I mentioned that is because now let's go back to what we were talking about before, when we have this basis of polynomials p sub j, and we're going to associate them with some compact set in a second. Okay, so if we took a basis of polynomials for the basis for the polynomials degree at most n, and we form this function b sub n, the sum of the moduli squared of these basis guys. Okay, well, if you've seen something like this before, that is, if this basis were an orthonormal basis for the polynomials degree at most n in for L2 of some measure supported on K, and think of a probability measure on K, then this b sub n is nothing more than what we might call the nth Bergman function for this measure mu on K. That is, if you form this sum of the pj of z's, pj of zeta bars, that's the reproducing kernel for point evaluation at the point z for polynomials degree n in this space. So it's not too hard to see that in this situation, this function phi sub n up above is related to b sub n. Its square is no bigger than this dimension of the space of polynomials degree at most n, m sub n times b sub n. That simply follows from the reproducing property of this kernel. Okay, and actually there's an inequality in the other direction too. That is, if you're looking at the polynomials degree at most n, that's a finite dimensional vector space. So any two norms are equivalent. So sup norm and L2 norm are equivalent. So there's some constant, which I'll call capital M sub n. So the sup norm of the polynomial degree at most n is no bigger than this capital M sub n times its L2 norm. And using that, you get an inequality the other direction, that this b sub n, the sum of the moduli squares of these pj's, is no bigger than, well, some constant, kind of little mn and big Mn times phi sub n squared. Now remember, little m sub n was the dimension of the space of polynomials degree at most n, and it grew like n to the d. So in particular, the nth root of little m sub n goes to 1. If this capital M sub n also goes to 1, we call, if first of all, if that happens, we call mu a Bernstein-Markov measure. These are very prevalent in the literature. If you have this property for your measure, then from the fact that these phi n's have the property that 1 over n log phi n converge to v sub k locally uniformly, then you'll have the same occurring for the 1 over 2n log b sub n. So they'll converge locally uniformly to this extremal function v sub k. So this deterministic property that this sequence 1 over 2n log b sub n converges to this extremal function v sub k in some fashion is going to be crucial for what we're going to do in the rest. Okay? If you just had L1 loc convergence of this 1 over 2n log bn sequence to v sub k, then of course then any linear operator acts nicely. So in one variable, the Laplacian of those guys would converge to that equilibrium measure mu sub k, the Laplacian of v sub k. In higher dimensions, DDC of that sequence would converge to DDC of this extremal function v sub k. But what we are really interested in is convergence, not of just the 1 over 2n log bn, but that full sequence of random plurisubharmonic functions, that full sequence 1 over n log mod hn to v sub k in some appropriate sense. I apologize, this remark at the bottom is completely out of order, but I didn't have any room to put on other slides. I didn't want to add an extra slide just for the heck of it. So I will just remind you that in one variable, if you take this Green's function, v sub k, it grows logarithmically, and if you subtract log mod z, then at infinity, this difference actually has a value. If you like, the limit as you go to infinity of this difference has a value called the Robin constant of the compact set K, and that's the same as minus the log of the capacity of K. Okay, so just a reminder, and you'll see this, something related to this coming in later. Okay, so what about these coefficients, these IID coefficients, these things I called AJs before? Well, again, I remind you, again, just to recap where we're going, we understand why we want to have deterministic asymptotics of this deterministic part 1 over 2n log bn because of this upper bound on our u sub n's, right? This 1 over n log mod hn, this blue part, this, excuse me, probabilistic part, plus this red part, the blue part, the probabilistic part, plus the red part, the deterministic part. So that if we have the blue part going to 0 in an appropriate probabilistic sense, in probability or almost surely, then at least we'll have the right upper bound if we have a good bounds on the deterministic part. And here's the reason, or here's some motivation for the following conditions on these independent identically distributed random coefficients. Okay, turns out that this piece here, that random piece, okay, if you have a condition which I'll refer to as finite logarithmic moment, and I should say finite logarithmic dth logarithmic moment, if you like, as if this expectation is finite, then the blue part, the probabilistic part, converges to 0 almost surely. If you have what I'll call a tail end condition, if the probability that this random variable is very big is very small with a precise decay here, then this blue part, the random part, goes to 0 in probability. And these facts are basically just from something we learned in measure theory, the version of Borel-Cantelli. Okay, so just remember that this finite logarithmic moment condition implies that our probabilistic part goes to 0 almost surely, and this tail end condition implies that the probabilistic terms go to 0 in probability. And the reason for the dth power here, if we're in CD, remember this really is because the dimension of the space polynomials grows like a dth power of the degree. So let me go back. Let's stick to one variable for a while. And one thing we want to do I'm not didn't give you any historical background of the theory of random polynomials. I would have said something about the Koch polynomials, linear combinations of the standard monomial z to the j, and then told you about some other work of Tom Bloom and Schiffman and Zeldich and others. But what people emphasized maybe in the beginnings of this stuff was when the basis polynomials were orthonormal polynomials with respect to some measure, like we talked about with these Bernstein-Markov measures before. One of the things we wanted to do in our work is go beyond the setting of orthonormal polynomial bases. So to motivate a little bit about what is known already in one variable, let's go back and recall some other standard potential theory. So let's let Tn tilde be the monic Chebyshev polynomial of degree n for our compact set K. And that means it is minimal sup norm among all monic polynomials of degree at most n. So the nth root of the sup norm of Tn tilde converges to that logarithmic capacity of K. So if you normalize this monic Chebyshev polynomial, T sub n here, so this T sub n has sup norm 1. So then that means that 1 over n log mod T sub n is a competitor for the extremal function. So it's certainly less than or equal to V sub K. And it's a standard result that, in fact, this sequence of subharmonic functions 1 over n log mod Tn actually converges locally uniformly to that extremal function, that Green's function, one variable, locally uniformly outside of the polynomial hull of the compact set. The set, all bets are off, or even on the polynomial hull, all bets are off. That is, you don't even have necessarily that this sequence converges to V sub K in L1 log. So you don't necessarily get these zero measures. Oh, sorry, this normalized zero measure. Got to get rid of this notation. Okay. Because just if you look at the standard example of the unit circle or the unit disk, these Chebyshev polynomials or their normalized relatives here are just the monomial z to the n. So of course, these functions just are equal to log mod z, and all the zeros are at the origin. But note two things. This will sound kind of redundant and maybe boring here. But if you look at the normalized Chebyshev polynomial here, the one that's sup norm 1 on the compact set, well, since it's sup norm 1, if you take 1 over n times the log of the sup norm, that's 0. These guys go to 0. And well, the leading coefficient is 1 over this sup norm of your monic Chebyshev polynomial. So since the nth roots of those Tn tildes go to the capacity, 1 over n times the log of these coefficients go to minus the log of the capacity. Well, these two conditions were generalized by Duncan Dauvergne there in your neighboring province of Ontario. Duncan is at Toronto. He defined a notion of asymptotically minimal sequences of polynomials. So Duncan defined a sequence of polynomials, we'll call them Q sub n here, and Q sub n will have degree n. He called a sequence asymptotically minimal for a compact set. This is in one variable. If, well, for some measure, in this case, it'll be a Bernstein-Markov measure, you have two conditions. You have a condition on the norms analogous to what we had up above here. 1 over n times the log of the norms go to 0. And you have a condition on the leading coefficients like we had up here, that 1 over n times the log of the modulus of the leading coefficient go to minus log of the capacity. And by the way, yeah, don't worry about this p so much. Think of p equals 2. But it turns out if you have a Bernstein-Markov measure, and I define that in terms of L2 norms, then it works the same with LP norms for any finite p. And here, if p is infinity, that means sup norm. So in any case, these asymptotically minimal polynomials generalize the Chebyshev polynomials in a sense. Chebyshev polynomials would be an example. Okay. Also, if you took an orthonormal basis for your polynomials in with respect to a Bernstein-Markov measure, that would work. But also all the standard named classes of polynomials from potential theory, Fekete polynomials, Leia polynomials, Faber polynomials, when they're defined, they're all in this category. In Duncan's theorem, Duncan's theorem in this case, now you'll see these probabilistic conditions coming in, is if you consider random polynomials, as we talked about in the beginning, where you take your basis polynomials to be asymptotically minimal, and your coefficients AIs here are again independent and identically distributed, okay, that you get almost surely weak convergence of measures of the Laplacian of 1 over n log mod hn to this Laplacian of v sub k, to this equilibrium measure, you'll get this weak convergence almost surely if and only if you have this finite logarithmic moment condition. And you'll get convergence, weak convergence of these measures to the equilibrium measure in probability, in the sense of improbability, precisely when you have this tail end condition. So in one variable, this is about as general a theorem as you can get. More general conditions on the you are allowed more general bases than just orthonormal bases with respect to Bernstein-Markov measures, and exactly the right conditions on the random coefficients to get, on the one hand, almost sure convergence, on the other hand, convergence in probability. Now, I'm just going to say a couple words about what Duncan did here, and then I'll jump to several variables. Note, if I put those two conditions of asymptotically minimal together, the condition on the norm and the condition on the leading coefficient, then that says that the monic guys, if you divide by the leading coefficients, the norms of the monic guys, when you take 1/n times the log, go to the log of the capacity. This condition by itself, as we've seen with the Chebyshev polynomials in particular, isn't sufficient to get L1 low convergence of this sequence of subharmonic functions, and hence it's not necessarily sufficient to get the convergence of the normalized zero measures to the equilibrium measure. You need an extra condition on what happens on the polynomial whole. And here's a deterministic theorem of Duncan's, that if you have a sequence Q sub n like this that satisfies the second condition, then if the monic guys on their norms go to the log of the capacity, if 1/n times the log of the monic guys actually get up to the log of the capacity in a lim-inf sense almost everywhere with respect to the Lebesgue measure on the interior of the polynomial whole of your compact set, then together with this other condition, then the normalized zero measures will converge weakly, the target measure, mu sub k. And so this is a deterministic result of Duncan's. And what he shows then, and this is one of the hard parts of his proof, is that the random HNs associated with this asymptotically minimal basis associated under the appropriate hypotheses on the ID coefficients will have this kind of lower bound property. So I'm not going to say how his probabilistic proofs go. I will just say that, well, the lower bound, this type of thing you have here, for the lower bound, for the convergence in probability, it's a little easier. He uses what's called the Kolmogorov-Rogozin concentration function inequality. And I'll just ask you to refer to his paper. For almost sure convergence, he uses a deeper result, a so-called small ball probability result from Nguyen and Vu. But look at the red. This is I want to concentrate on. In general, in this subject, upper bounds on these sequences of random subharmonic or plurisubharmonic functions are fairly straightforward, and they're going to follow from the appropriate hypotheses you put on the IID coefficients. But lower bounds, like we just talked about, they're generally more difficult and require some heavier probabilistic tools. Of course, now we're going to jump to higher dimensions. And higher dimensions, well, zero sets of polynomials are a little more complicated than the finite points you have for zeros of a polynomial in one variable. So we're going to need a more flexible deterministic result on L1 low convergence for a sequence of plurisubharmonic functions in our Lalong class to our extremal function v sub k that we have in this one variable setting. And here's what we're going to use. Here's our main deterministic tool. And it's actually, this is simply a result about subharmonic functions on a domain in Rn, but I'll state it for our setting. So suppose we have a sequence of functions, I'll call them u sub n to keep our notation, in this Lalong class. So for us, plurisubharmonic functions of logarithmic growth. And suppose it's locally uniformly bounded above. And suppose there's some continuous function in the Lalong class so that the lim sup of this sequence is below this continuous guy. For our purposes, this continuous guy v will be our v sub k, for appropriate compact set k. And suppose we actually hit this function v at a countable dense set of points, a limiting sense, pointwise. Then we get L1 low convergence of the sequence un to v. This is not a deep result, and it's really a result about subharmonic functions, but this is what we're going to use. And to emphasize the red upper bound theme here, again, under appropriate hypotheses on our IID coefficients, we'll get these first 2 points, the upper bound, so to speak, for our associated random plurisubharmonic functions in our long class. So let me go back to one complex variable for, 2 minutes to motivate what we're going to talk about in several variables. So let's actually look at a special case of Duncan's asymptotically minimal. This will be kind of the L infinity version, which is called asymptotically Chebyshev. So, of course, remember those Chebyshev polynomials? Well, when you normalize them, 1 over n times the log of t sub n, these guys go to this extremal function locally uniformly outside the polynomial hull. But we'll call a sequence of monic polynomials Pn tilde of degree n asymptotically Chebyshev for k if, well, they act like Chebyshev polynomials in the sense that the nth root of the sup norm of the nth guy goes to the capacity. And well, for such a sequence, these subharmonic functions 1 over n times the log of these normalized Pn tildes are competitors for the extremal function v sub k. So this function I've called u, the lim sup of that sequence, when I take the regularization, is below v sub k. But because of this condition, you actually get that at infinity, u of z has exactly the right growth. That is, u of z not only grows like log mod z, but u of z minus log mod z has a limit at infinity that's exactly the same as you have for the extremal function. And that tells you that this function u actually equals this extremal function outside the polynomial hull. But again, it's a lim sup of a sequence that you're taking here, and then you're regularizing. So this notion of asymptotically Chebyshev, we're going to generalize to several variables. And how do we do that? Well, we've got lots of Chebyshev polynomials. So here's what we're going to play with. So we're going to look at multi-indices alpha. So if you take a monomial in several variables, and here think of C2 for the moment, so z to the alpha, then that means z1 to the alpha 1 times z2 to the alpha 2, et cetera, times zd to the alpha d in d dimensions. So alpha we're using is this multi-index, alpha 1 through alpha d. Okay, so we're going to order these multi-indices so that well, they go by increasing length, and if you have, and this will give you an ordering on the monomials themselves. And so if you look in terms of monomials, you're ordering by increasing degree, and within a given degree, use something like a lexicographical order. So here I've chosen Z1 to come before Z2. So for example, in C2, I go 1, Z1, Z2, and then for the degree 2 guys, I take Z1 squared, and then Z1, Z2, and then Z2 squared, and so forth. Okay, and I list these. Okay, so I'll call this ith guy in the list E sub I. So for example, if I've counted right, the Z1 squared Z2 is the 8th monomial in my list. So E sub 8 is the monomial Z1 squared Z2. Okay? With each monomial, with each of these E sub i's, or with each multi-index, if you like, I'm going to associate an analog of a monic polynomial class, in the sense I'll take the class that consists of E sub I, this ith monomial, plus a linear combination of the guys that come before it. So for example, this 8th class would be all polynomials that form Z1 squared Z2 plus a linear combination of the previous 7. And so for each such class, I define a Chebyshev constant. I minimize the sup norm over all polynomials in that class. And I'll call that number tau sub alpha I of k. Okay, so tau sub alpha of 8 would be the smallest, well, you get it, right? Okay, so again, these classes are analogs of monic classes, monomial plus now linear combinations of previous guys, just in higher dimensions. And I get one number, given a compact set, I get one number for each monomial, for each class. I'm going to do something with all of these Chebyshev constants. I'm going to form new Chebyshev constants called directional Chebyshev constants. So what do I do here? And this is an idea, it goes back to Zaharucha. If I take a multi-index and I normalize by dividing by its length, for example, I take that 8th guy, I take 2 comma 1, 2 plus 1 is 3, so I form this new normalized guy, 2/3, 1/3, that gives me a point on the standard simplex in RD, standard D minus 1 simplex in RD. So just think D equals 2. So the standard 1 simplex is just the segment connecting 1, 0, and 0, 1. Okay, so you're getting points whose coordinates add up to 1 on this line. So 2/3, 1/3 is a particular point. Okay, so I'll call such a point theta. Okay, and if you look at points on this simplex except on the so-called boundary, so I've looked in this two-dimensional case, I look at all points except 1, 0, and 0, 1. That's what this sigma naught is. Zaharucha showed if you fix a theta on that sigma naught, then you can define a directional Chebyshev constant. Well, you can define a directional Chebyshev constant by taking a lim sup. Tau k theta would be the lim sup of the roots of the appropriate standard Chebyshev constants, where you look at these Chebyshev constants corresponding to indices that go off in that direction. So for example, if my theta were 2/3, 1/3, right, I would look at the standard Chebyshev constants corresponding to those polynomial classes that start with monomials like z1 to the 4th, z2 squared, z1 to the 100th, z2 to the 50th, but even things close, z1 to the, I better be careful here, z1 to the 50th, z2 to the 26th would be close enough, right? And Zaharucha showed that actually the limit of the roots of those appropriate guys exists. Okay, so you get the idea. I've got this whole sequence of Chebyshev constants, and now with each point on this simplex, I just look at sequences, subsequences from that sequence, whose normalized exponents, if you like, go off in that direction. That's what this tau k theta is doing. Okay, so in this two-dimensional setting, I've got a kind of one parameter set of these numbers tau k theta. Is it okay with everybody? So if I take one of those points, theta in sigma naught, we'll call a sequence of polynomials that are that recover that directional Chebyshev constant in the direction theta. We'll call a sequence theta asymptotically Chebyshev. If they do what I just said, that is, well, they should have their, these q sub k's are monic in the appropriate sense. They're in these classes, but these classes so that you're looking at the exponents that are going off in that theta direction, and they're asymptotically Chebyshev in the sense that the roots of their sup norms do go to this tau k theta. Okay, and now suppose we have one polynomial from each of our monic classes, so one polynomial for each associated monomial. Then we'll call this sequence q sub j asymptotically Chebyshev for k without any extra adjective, if for each theta in sigma naught we can find a subsequence, which is theta asymptotically Chebyshev. So we can recover all the directional Chebyshev constants from subsequences of this full sequence q sub j's. An example would be if I simply took all those Chebyshev polynomials for each of the monomial type classes. So this is an analog or generalization of asymptotically Chebyshev from the one variable case, a complicated one admittedly, but it has similar properties as Tom Bloom showed about 20 years ago. As if you take an asymptotically Chebyshev sequence for the compact set K, and you form this sequence of subharmonic functions, 1 over degree times the log of the modulus of the normalized version of the q sub k's divided by their sup norms, then that lim sup, when you regularize, equals the extremal function v sub k outside of the polynomial whole of the compact set. So you get the same type of conclusion as you have in the one variable setting. I'll say something about the proof here, but I think I should also give you, along with the collection, the example of the collection of all the Chebyshev polynomials, other examples of asymptotically Chebyshev sequences for k. Okay, so as I said, you could take the full quota of standard Chebyshev polynomials for each monomial class, but you could also take, going back to our measure situation, if you have a Bernstein-Markov measure on your compact set, you could take the L2 minimal polynomials in each of those polynomial classes. So these would be orthogonal polynomials with respect to this measure, right? Just like you would do in the one variable case. And these would be asymptotically Chebyshev. But there are also generalizations of Fekete polynomials and Leia polynomials from the one variable setting that you can find in, well, Tom's paper in the IU Math Journal from 2001. So there are other interesting examples besides these two. But let me give you a few sentences about the proof of this. Again, here's the statement that if you have this asymptotically Chebyshev sequence, then the lim sup of this sequence hits v sub k, at least pointwise outside of the polynomial whole of the compact set. And well, the left-hand side is smaller than the right-hand side simply because each of these guys is a competitor, right? And so just as in the one variable case, the lim sup is going to be smaller than v sub k. So how do you know you actually get up to v sub k outside of the polynomial whole? Well, as we said briefly in the one variable setting with asymptotically Chebyshev polynomials, to do with the asymptotics. And if you have a function of this long class, logarithmic growth, well, in several variables, if you subtract log mod z from this function, you might not have a limit at infinity. I mean, you can get different limits in different directions, basically. But a long time ago, some people defined what's called a Robin function associated with the function of this long class. So it's a new function of z, which you get by doing the following. So think of the following. If I fix a point z, think of z on the unit sphere for the moment. Think of z as a unit vector. Then I look along the complex line tz, complex line in the direction of z. Well, along there, then I have a subharmonic function of logarithmic growth. So it's possible if I take u of tz and subtract log mod t, I might have a limit as I go off, as I let t go to infinity in modulus, right? Well, might not, but I can at least take the lim sup. And that's what rho sub u of z is. Okay. So a priori, think of this as defined on the unit sphere, but with my definition here, it's actually logarithmically homogeneous and gives you a function all of CD. But it obviously detects something about the asymptotics of your function u, its behavior out at infinity. What Tom Bloom observed is that if you have a function in the low long class that's a competitor for the extremal function for k, that is, if it's less than or equal to 0 on k, so i.e. it's less than or equal to v sub k, if it has the same asymptotics as v sub k, that is, if its Robin function agrees with that of the Robin function for v sub k, then actually it equals v sub k outside of the polynomial whole. Again, on the set compact, on the set k and on its polynomial whole, all bets are off. This uses a very deep result of Bedford and Taylor from the late 80s, an integral formula is in their Enel Institute Fourier paper, plurisubharmonic functions of logarithmic singularity. It's a very deep result they use, but you get this nice conclusion. If you have the same asymptotics as the extremal function and you're a competitor, then you agree with that extremal function outside the polynomial whole. So if you think about what we're doing here, well, a function like this, oh, sorry, you probably can't see my cursor. Maybe you can. This 1/degree qj log mod qj or supernormal qj sub k, right? For one plurisubharmonic function like that comes from this polynomial q sub j, it's pretty clear what its Robin function would be. You would just replace that q sub j by the top degree homogeneous piece of q sub j. That would detect the asymptotics. That's what I'm calling q sub j hat. And so this thing on the left is essentially the Robin function of our left-hand side. And so what the hard part of Tom's proof was to show that indeed this Robin function, left-hand side, agrees with the Robin function of v sub k. Well, again, I'll let you read his paper. It's not at all obvious. That's a lot of work. I wanted to show you an outline of the proof anyway, at least see the analogies with one variable. And now I can finally tell you what we've accomplished randomly in a sense. Okay. So what we considered, again, to generalize the situations from orthonormal bases, we wanted to consider the situation where we take an asymptotically Chebyshev family for our compact set K in its higher dimensional setting. And we'll take this asymptotically Chebyshev family and normalize to get polynomials Pj whose supernorm is 1 on K. And then using these Pj's, we form, for each n, we form the function b sub n, as we did before, the sum of the moduli squared of the Pj's. Okay? And now we have a deterministic proposition for this sequence of functions b sub n. excuse me, we have the following, again, starting with this asymptotically Chebyshev family. Given any subsequence, there's a further subsequence and a convolutional dense set of points, so that these 1/2n log b sub n's on this further subsequence hit v sub k at all points in this convolutional dense set. So again, you see subsequence of subsequences. Remember, this is going to be related later on to a convergence and probability result. Gives you almost immediately that this sequence of plurisubharmonic functions 1/2n log bn in this setting do converge to our extremal function v sub k and L1 log. You basically can't do any better. You can't even get pointwise convergence, and you can't get the full sequence to converge. So this is about as good as you can expect. So this is a deterministic result about the 1/2n log bn's once you have an asymptotically Chebyshev family. Now, to put this together to get a probabilistic result, now we're going to consider random polynomials. Our random polynomials h sub n of degree n will use these p sub j's, these normalized polynomials from asymptotically Chebyshev basis. And the AJs are, again, IID random variables. And so using these propositions from before and the same type of ingredient that Duncan used and Duncan and Tom used in an earlier paper, this Kolmogorov-Rogozin concentration function equality, we have the following result, that if our coefficients AJ, our IID random variables, satisfy this tail end condition, then we do get in probability our sequence of random plurisubharmonic functions 1/n log mod hn do converge to v sub k and L1 log. That allows us to say something about the normalized zero measures. And obviously I'm concentrating on the deterministic stuff in this talk. Let me just say, so I think I've done 50 minutes. Let me just give you 2 minutes of what we've started to do on the almost sure convergence. And this is not the whole story, but we don't have much of a story here. For almost sure convergence, again, let's let HNs be like they were before, except now, okay, I don't want to lie to you. The result on almost sure convergence, at the moment, we need to assume that our bases PJ have a good property in the sense that we get that the corresponding sequence 1/2n log bn converge to v sub k locally uniformly. We need the stronger convergence, which happens, for example, if these PJs are orthonormal with respect to Bernstein-Markov measure, but not for asymptotically Chebyshev case. But if you have this, then we can prove the following. Our random variables satisfy that finite logarithmic moment condition plus something else if these AJs actually have a bounded density. So they're random variables that form some bounded function times Lebesgue measure here. With these conditions, then we can get the almost sure convergence 1/n log mod hn to v sub k and L1 log. And hence we'll get the convergence of the currents DDC 1/n log mod hn to DDC v sub k. And you might say, well, geez, why do you want this second condition? Why do you have this second condition? Well, we probably don't need it, but let me just say one word. When we started working on this, we had hoped to deal with.
Sorry, M and Z is Lebesgue measure for distribution.
Pardon? Yeah. This is Lebesgue measure. I'm sorry. Yes.
Okay,
Sorry about that. Yeah. So I should have said yes. The reason this strong condition was put here was we were actually considering, and I think in my title I even had random polynomial mappings in this as part of the abstract. We wanted to consider what you call the higher codimension case. That is, instead of considering just a random polynomial, you can consider an M tuple of random polynomials and their common zero set. So this would be a higher codimension algebraic surface in CD. Okay, and in this case, though, what the analogous target would be, well, so the corresponding basis polynomials for each of these random polynomials, these component random polynomials, could come from different bases related to some other compact set. In any case, what you end up doing here in this case is studying a wedge product of currents So you have a wedge product of DDC 1 over n log mod h's for your random polynomials. So in order to just have something like this wedge product to make sense, in the sense of currents, you need something, and we need something to happen. So this condition on this second condition on phi having an absolute continuous bounded density makes this random current have a sense almost surely. Okay. But in any case, we don't have any results in this higher codimension case. We conjecture that if in particular we had the right convergence of the corresponding 1 over 2n log bn's for the component guys, then we would get the corresponding almost sure convergence of the currents. But since I've already taken more than 50 minutes, I think I'll just say that L1 low convergence is certainly not enough. We need to have more. So thank you very much for your attention. And please, if you have any questions, I'll be happy to try to answer them.
Start by thanking Norm for his talk. Are there any questions or comments?
Oh sorry. Yeah, okay.
I actually have some questions that I have to apologize because I was teaching just now, so I got in at the tail end of your talk.
Oh, hey,
what
Steve.
what is asymptotically Chebyshev?
Oh yeah, I'll go back here. Yeah. So this for us in several variables, it's something that Tom Bloom defined way back when. So remember, these directional Chebyshev constants, Steve? You've seen that, right? Because you've dealt with transfinite diameter before, right?
Mm-hmm.
Okay. So it just so Tom called it, if you take a point on your standard simplex, and if you have a sequence of polynomials that are theta asymptotically Chebyshev, that just means that they give you that directional Chebyshev constant, right? They're normalized in the right way, and they give you the directional Chebyshev constant with their sup norms.
Mm-hmm.
And asymptotically Chebyshev for K simply means you have this sequence of polynomials such that for any point in the interior simplex, you can find a subsequence that's asymptotically Chebyshev for that theta. So you can recover all these directional Chebyshev constants.
Okay, that'll require some studying. The other question was, well, you got this convergence of this BKs to VK or log BK to VK or something on a countable dense set, I believe, right?
Yeah.
Do you have any intuition for what that set is?
Ooh. You mean, can you actually construct a set? Is that
Characterize it in some way? And I mean, can you do better than that? Is it better than just a countable dense set?
I don't know, but you can't get pointwise convergence necessarily everywhere. Can you get bigger than countable? You want bigger than countable, but you can't.
Yeah,
you can't
just
get
some
everywhere.
idea about why you only get countable dense.
No, I mean, it's just kind of a standard. It's not really. It's just a standard thing about coverings and taking subsequences. So it really doesn't give any feel for how big the set could be, but
it's like a diagonal argument or something.
Yeah, like that. Yeah, but you certainly cannot, even with this nice condition, even in one variable, you can't get pointwise you can't get pointwise convergence everywhere. That's for sure. Can you get bigger than countable? Whatever that means, I don't know.
Can you just like in 1 minute explain why that's sufficient to prove L1 log convergence?
Well, it's probably because to show L1 low convergence, you want to show that again, it's related to, again, taking subsequences. You want to show every sequence for every subsequence of this guy, you can get a subsequence that converges.
Oh, I think I understand.
That's all.
I think I understand. You have a uniform upper bound or something on the left side, and
yes,
you have some sort of compactness there.
Yeah. So
and then you just get convergence in L1 look, if you don't go to minus infinity, that kind of argument.
Right. And here, like I said, this is our standard proposition, right? It's just about
right.
sum of
Okay.
functions. Okay.
Right. Okay.
It's just with the upper bound and
yeah.
complement
Okay.
set.
I see. Okay. Thank you.
Mhm.
Are there other versions of the results where you put other hypotheses on the coefficients AI and then get other kinds of convergence?
Well, this, oops, sorry, where am I at here? Let me go back here. In the scheme of things, Maxime, that's, I'm not sure exactly how to answer that. But if you, for these two modes of convergence, almost surely in improbability, this theorem of Duncan's in one variable tells you these are the best possible. They're actually if and only if, in the sense that if this doesn't hold, then he can show that you don't get convergence to this measure. Okay, but I would defer to experts if you want to go to other modes of probabilistic convergence. Steve, maybe you can, or Tom Bloom, if you're there, you could help me here. Beyond almost sure and improbability, I don't know what else. I don't know about results on what would you aim for, or other results with respect to the coefficients.
You look at a real variable, how much more complicated things become.
When you say real variable, are you talking about real zeros? Is that what you?
Yeah, I guess. Yeah, and also, I mean, AJs are real valued. It's
well, first of all, I mean, these AJs could be real value, just more generally have a complex, right? But there, with respect to, there's a lot of work on, there has been a lot of work classically on real zeros of random polynomials in one variable, the whole literature on that Steve, Tom, you guys know this better than me, but you know, what is there something like there's like for the Koch polynomials in the standard setting, you get like a log n real zeros or something like that. Is that?
Yeah, I mean, so that's why I'm saying it's kind of, it's not as nice as the complex case.
Right. Yeah. Well,
but in many variables, have people thought about it?
Well, I'd make a comment that there is a vast literature in higher dimensions in the real case, but you cannot use any of the techniques of this talk. Even though I only saw the last 15 minutes, I can guarantee you can't use any of the techniques of this talk because you don't have any of these Fourier subharmonic function things or any of the complex analysis. You have to use Katz-Rice type formulae, which are very, very complicated.
Any other questions or comments for Norm? All right, let's thank Norm again.